All right, so we're going to talk about the toolbox functions here. These are kind of your most basic functions, also known kind of as our parent functions, and then we will transform them using various techniques here. Some vocab that we need to know, though, is endpoint or initial point, vertex, and inflection point. These are based on whatever kind of graph we have. So like an endpoint and an initial point would be on a square root function. A vertex you would find on parabolas and absolute value graphs. And inflection points are ones that you'd find on like cubics, cube roots, and things like that, where the ends are going opposite directions. And so it's kind of where we change that. So we're going to introduce the very beginning of the toolbox functions. I would highly recommend writing these down. And if you're one of the students in my class, you should have received a sheet that you can take notes on this with. So our first function that we're going to talk about is our constant function. The constant function means it's never changing. It is purely constant. So if I were to look at a graph, it's this graph right here, where it just goes left to right. Our parent function is just y equals 1, and our transformed function is y equals k. So this could be anywhere. This just happens to be the most basic parent function, but it could be y equals 3, y equals -5, various things like that. Our domain would be negative infinity to infinity, because if you remember, domain is left to right. In our range, it does not go up and down at all. It is just 1. So we've got y is 1, basically, is our range. And then for college algebra here, the way we do our end behavior is very, very basic. Our ends here, what are the ends doing? Well, the end is going left and right. So our end behavior is left-right. The next one we're going to talk about is linear. This is one that is probably most familiar to everybody because we spend a large amount of time on this in Algebra 1. It is a line, and this one is the parent function. Notice it's just going up 1 over 1 every single time. So our parent function is just y equals x. It goes through our origin point, has not moved up and down, and goes from the bottom left to the top right. Our transform function, I'm giving you two different ones. The most traditional one people know is y equals mx plus b, where m is your slope and b is your y-intercept. However, when we're talking toolbox functions, we look at this a, this h, and this k. The a determines like our steepness and direction, and then the h and the k tells us where does the center 0, 0 point get moved. And that's true on all of these functions. Our domain, once again, our x values, negative infinity to infinity, and our range is going to be the same. Now our end behavior, we can look at this side and say, okay, the left side is going down, and then it's going up. So it's down, up. The next familiar one should be quadratic, because we spent a lot of time in Algebra 2 talking about quadratic functions. And if you recall, this is actually a parabola. So it's this little graph right here. The parent function is y equals x squared. And our transform function uses that a, h, and k again. So this h and this k tells us where does this 0, 0 point move. And so that actually is our vertex. Our domain, as we go from left to right, is negative infinity to infinity. Our range starts at 0 and moves up. Notice there isn't any negatives here. And actually, I can tell you, I already see an error on that, but I'll have to fix it later. Well, actually, I'll fix it right now. This should actually be, hold on. This should be a bracket because with our domain, it can equal 0. And then our behavior, end behavior is up, up. So make sure we have this bracket here because like I said, there is a point right there. Our next one is cubic. I like to think of this as the bumpy slide, you know, from grade school, the one that always hurts your tush. And then our parent function is just y equals x cubed. Our transformed function should be familiar. The things that are changing, we're just adding this a, h, and k. And I do want to point out that our domain and range and our end behavior are all based on this parent graph, on this parent function. So the transformed function will have different domains and range possibly. So our domain of this is negative infinity to infinity. Our range would be the same. And then our end behavior here would be down, up. And then our next function is going to be our square root function. And our parent function is just y equals the square root of x. And it looks like what we call a one-wing graph. So if you think about birds you make in grade school, so there'd be another half here, it's half of a bird. It's one wing of it. So a one-wing graph. Our transformed function looks like this. It is possible that the a is inside as well, in which case you'd have to factor some stuff out to actually put it in this form. And then our domain starts at 0 and goes to infinity, and our range does the same thing. And our in behavior here, since this is an endpoint and these are arrows, our in behavior is going to be up and to the right here. Then we have a cube root function. So y equals a cube root of x. And then our transformed function looks like this. Our graph is just another version of that bumpy slide, just going a little bit more sideways than the cube. Our domain and range are both negative infinity to infinity. We've got arrows on both ends. While it is going up slowly, it is still going up all the time. And then our in behavior is down, up. So this side is down, this side is up. And then our last one of today is our absolute value function, which is y equals absolute value of x. The transformed function looks like this, and once again, the a could be inside on all of these. So our graph is a V, and then our domain here from left to right is negative infinity to infinity, and our range starts here at 0 and moves up. So it is 0 to infinity, and then our in behavior is up, up. And feel free to pause if you still are trying to catch up on all your writing and rewatch these parts if need be. So let's move on to a couple examples. Here's our first example. So we're going to graph the following function. So identify the x and y intercepts, the vertex, domain and range, and in behavior. I'll start with the vertex because to me that's the easiest one to see. If you recall with our formula, we had in this location, let's see if I can just rewrite it above here, we had a x minus h squared plus k. So we have an x and a minus, so here's our h, and then our k is this right here. Here's the way I think about it. Our h is always whatever is the opposite of showing here. Right now it looks like a -4. That means our h is a +4. And h and k is our vertex. K, since it says plus k, this would be the same as saying plus and -2. So our k value is -2. If I were to go ahead and graph that, 3, 4, down 2, here's 4, -2. Then I could find the x-intercepts, the y-intercepts, domain, range, and behavior. I can look at the in behavior of this and see since a is positive, that means it's still following our same general thing. So I know my in behavior of this is going to be up, up. Let's find the x-intercept. To find the x-intercept, we plug 0 in for our y value. Let's see if I can fit all that over here. So I'll have 0 equals 3x minus 4 squared minus 2. And now I want to solve for x. So I'd add 2 and divide by 3. So I'll have 2/3 equals x minus 4 squared. Now to get rid of the square, I'm going to square root. Now I'm going to go ahead and flip these around here. I'll have x minus 4 equals plus or minus the square root of 2/3. And if I go ahead and square root 2/3 down to a decimal, it will help because since we are graphing, it really doesn't matter if you leave it exact or not. But I will have two equations because of this plus or minus. I'm going to change this over here and do this over here. So I'm going to have x minus 4 equals a positive 0.82 and x minus 4 equals a negative 0.82. Let's go ahead and solve this. So x is going to equal 4.82. And if I add this over here, x is going to equal 3.18. Those are our x-intercepts. I'm going to write that right here. Actually, let's pick the same color. I'm going to write it underneath since I kind of don't have enough space. So 4.82 and 3.18. If I were to estimate, 3.18 would probably be right here. 4.82 is going to be over here, which looks good because then our vertex is in the center. Now let's find our y-intercept. To find our y-intercept, we're going to plug 0 in for the x. That means I'll have y equals 3 times 0 minus 4 is a negative 4 squared minus 2. Negative 4 squared is 16, times 3 is 48, minus 2 is 46. Here's the problem. I'm going to go and put this here. My y-intercept is 46, but I can't go 46 on my graph, so I'm not going to be able to graph that. The next thing I'm going to do is probably find some points that I can actually put in for this, which means that I'm going to type into the calculator the equation into the y equals, and then I can use the graph or the table function and actually find some points. You could also do all these points by hand. That is entirely up to you. All right, so I got 3 is 1. That means 5 is 1. 6 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I figured that was the top one, but just in case. That means that 2 would be 10. And then we can sketch this. Bear with me on my sketch here because graphing on a computer, very difficult. There's that side. Woo-hoo. Okay, that was a terrible graph, but you get the idea. The next thing we're going to do is find the domain. Our domain, as we go from left to right, is negative infinity to infinity. And then our range, we are actually starting right here. So our range would be y starts at -2 and goes to infinity. All right, let's see our next example. This time we have a cube root. Let's try this again. As I pointed out on the thing, remember I said that a could be in here somewhere. We just have to factor it out. So let's factor it out to start with. That means I'm going to have a -1, and then I'll have an x minus 3, all under this cube root. What that does is allows me to say, okay, this is my h, this is my k. My inflection point would then be 3, -1. You do have to factor this out to be able to see that h. All right, let's find the x-intercept. Our x-intercept is found by plugging 0 in for y. So we'll do that over here. So 0 equals 1/2 cube root of -x plus 3 minus 1. If I were to solve this, I'm going to add 1 and multiply by 2. So I'll have 2 equals the cube root of -x plus 3. I cube both sides. 8 equals -x plus 3. Subtract 3. 5 equals -x. X equals -5. That means my x-intercept is -5. X equals -5. Let's go ahead and graph these few points that I have. So 3, -1. My x-intercept is -5. 1, 2, 3, 4, 5. Let's find the y-intercept. That means I put 0 in for the y, or sorry, 0 in for the x. Y equals 1/2 cube root, 0 is in the x, so I'm really going to have the cube root of 3 minus 1. So 0.5 times the cube root of 3 minus 1. That would be our exact form, by the way, but our approximated form would be a -0.28. Y equals -0.28. -0.28 would be somewhere in here. We can kind of see that that's at least in the road. And then we're going to plug in some points and actually see what are some of the other points we could graph. And this is where it can get a little bit more difficult with roots because our numbers don't always come out that nice. You may have to graph some estimated numbers here, but let's see what we come up with. So 1 is ugly. 2 would be a -1/2. 2, 3 should be a -1. 4 is negative 1.5. 5's not good, 6 not good, 7, 8, 9, 10. Okay, 11. We don't go to 11, but I'm just going to go and do 10. 10 is negative 1.95, so that is almost a negative 2, basically. And then just to help my graph out, I'm going to go ahead and graph a negative 10, which would be a 0.17, so it's barely up here. Then we're going to do our best to graph this thing on a computer, which is not the easiest thing in the world. That is not a good graph. I apologize at the lack of smoothness of my graph. All right, but roughly speaking, that is your graph. Now let's find the domain. Our domain, as we go from left to right, would still be negative infinity to infinity. Our range is actually going to be the same thing because we have arrows moving up and moving down. And then our end behavior on this one is actually the left side is going up and the right side is going down. So our end behavior would be up, down.